Okay, so let's get started. This week will be mainly devoted to guest lectures for these applications of one you should choose for your third part of the project. So today I will start with continuing to talk a little bit about retransmission protocols, but after the break we will have a guest lecture about e-health. And on Thursday we will have a guest lecture about how to use communication in control applications, and also a little bit on traffic safety and traffic efficiency. But for the first part here we will continue our journey throughout the protocol stack. We're still in the link layer mainly, but we talk about retransmission protocols. And as a matter of fact, these can be used at different layers. But typically, we would have retransmission protocols at the link layer. All right, so let's get on with things. So what we talked about last week was to talk about these ARQ protocol. ARQ stands for another word for retransmission protocols. So these are then implemented at some layer. Okay, so suppose we have layer 3 here. We could have layer 2 also if you like, or layer 4. But just for simplicity, say that we implement this in layer 3. Then the objective of the protocol is to provide a service, and provide a service now to layer 4. Okay, so if the protocol is in layer 3, it would like to provide a service to layer 4. And what we want to do is we want to have error-free transmission of service data units. And they should be delivered also in the right sequence and without duplications. So that's what we want to do. Now, one way to measure how good of a job we do is to measure what's known as the effective data rate of the service. Okay, so this is the data rate which layer 4 in this case is experiencing. Okay, if we're layer 3, we provide a service to layer 4. So the data rate provided then to layer 4 can be computed as the following: is the effective rate. It's the number of bits that's in a service data unit divided with the time it takes to deliver that service data unit. Okay, so it's the ratio of these two things. So if layer n-1, the layer below us, so just to make sure that if we have layer 3, the protocol where we have the retransmission protocol, we provide a service to layer 4, but then we use layer 2 in this case in order to actually transmit the bits. So if that has an effective rate of r bits per second, then we can compute the efficiency of our protocol as the ratio between the effective rate, the rate that we provide up, divided with the rate that we get from below. And this is something which is less than 1. I mean, obviously, we would like this to be as close as 1 as possible. And if we want to write this in terms of the efficiency, then the effective rate is the efficiency times the data rate of the layer below us. Okay, so we would like the efficiency to be high here. Okay, now for stop and wait, we did a rather careful analysis of what the efficiency is. And if we have the transmitter and receiver, we do some timing diagram like this. And the important thing is to figure out, okay, how long does it take from when we initiate transmission of a data frame until we can start to transmit the next data frame. And that is T0, also known as the turnaround time or the reaction time. This is the time it takes until we are ready to transmit the next service data unit. So this will be then the denominator when we calculate the effective rate. Okay, so a little bit more in detail. So this turnaround time consists of propagation delays. It consists of the time it takes to transmit the frame duration, some processing time, the time it takes to transmit an acknowledgement, propagation time again, and some processing time. So we add everything together and we get then the turnaround time. So the effective rate for stop and wait, and the 0 here simply means no errors. Okay, so it's the best we can hope for. There are no errors when we transmit the frame and no errors when we transmit the acknowledgement here. So then it's essentially the number of useful data bits in the frame, which is the information frame here. The data frame has NF bits, including NO overhead bits. And the overhead bits is sequence numbers, addresses, CRC check bits and whatnot. Okay, so things which are not useful data for the layer above us. So we take NF, we subtract NO and divide by T0, and then we get R times the efficiency, and then this is the expression we get. Okay, so that's where we ended last time, and let's now continue. And okay, well, now, so what could make the efficiency be small here? Well, there are many things that can make it small. We have a penalty here, which has to do with the overhead of the protocol. We have a penalty here, which is due to the overhead of sending an acknowledgement. But we will concentrate our attention to this term here, which is 2 times tprop plus tpros divided by nf and multiplied with r. And if this number within the red box here is a large number, we see that the efficiency is small and the effective data rate is then reduced compared to the data rate that we have in the layer below us. Okay, and this could be large if the propagation delay plus the processing delay is significant compared to the time it takes to transmit the frame. Because this, what's inside the red box here can be written as 2 times tprop plus tpros. Oops, I'm running out of space here. And then divide through by the time it takes to transmit the frame. NF divided by R is TF. Okay. So we see that if we have a lot of propagation delay and processing delay in comparison with the time it takes to transmit the frame, then the efficiency of this protocol is small. Okay. And the problem is essentially due to that once we transmit the frame, we have to wait a significant amount of time until we can transmit the next frame, under which the transmitter is idle. All this time here, the transmitter is idle, it's not sending any data. Okay. So from here, the transmitter is just waiting for the acknowledgement. And this is essentially wasted time. So the question is whether we can do better. Well, of course we can do better, but we can use this time to transmit the next frame instead of waiting for the acknowledgement of the frame we just transmitted. And that's the essential idea about using a protocol called go-back-n, where we continuously transmit frames and then keep track of the acknowledgements that come back. Okay, so to do that, we need some bookkeeping. We need to keep track of the frames that we have transmitted, and we need to keep track of the acknowledgements that we get back in order to not lose any packets or duplicate packets and so forth. And we will use something called sliding windows to do this. So that's essentially buffers, data buffers. They will contain packets or frames, and these frames will be enumerated with sequence numbers. And these sequence numbers will be actually included in the transmitted frame. So we want to keep the number of bits in the sequence numbers to be as small as possible in order to limit the overhead. Remember that the overhead is also hurting our efficiency. So what we do then in practice is we choose them to be m-bit numbers, and we want to keep m as small as possible. We will talk more about how to choose m a little bit later. We just accept now the fact that maybe we have 16-bit or 8-bit or 3-bit sequence numbers. Smallest we can have is 1-bit sequence numbers, is what we used in stop and wait. So if we have a send window, it has a certain size, 8 in this case and 4 in this example. If it's 4, it means that we have 2 to the power of 4, 16 sequence numbers These are the possible sequence numbers, and we enumerate them from 0 up to 15. Okay, so these are the sequence numbers that are here. We have a size 8 window, which means that at any given point in time, we can store 8 frames, but not more than 8 frames. Then we have 2 state variables, SF and SN. And SF is a pointer that points to the sequence number of the latest packet we have transmitted, the oldest packet we have transmitted. And SN points at the slot, at the sequence number of the next packet that we can put into the send window. So it denotes a packet that we not yet transmitted because we haven't received it from the layer above. Okay. At any given point in time, we can think of the sliding window here as being slided to this position, which means that everything to the left here, all these packets, all these frames have already been transmitted and acknowledged. So these have been delivered. Okay. Then we have a number of packets which are in transmission. We have not yet, as a transmitter, we're not sure about the fate of these packets yet. And then we have some space in our send window, which are packets which we have not yet gotten from the upper layer. Okay. These packets which are in transmission, we call them the outstanding packets. Okay. Now, we can now start to fill up this send window until we filled up the entire size of it, the full buffer, and then we have sequence numbers of packets which we cannot accept from the upper layer yet. Okay, and then we need one convention also. When the send window is empty, then we put SN equal to SF. Okay. Therefore, SF is not pointing at some packet which has been transmitted. It's just, hovering around until we have a packet to transmit. So when SF is equal to SN, there are no outstanding packets. So this is the initialization point, and also it could be like we empty the send window also. Okay, any questions so far? No, okay. So now, go back in. What is the main idea here? So if we remember, in the problem with stop and wait is this time. This time, the sender does nothing except waiting for an acknowledgement. So instead of waiting here, how about sending the next frame here? And the next frame, and the next frame, and then just keep track of the acknowledgement that goes back. So that's exactly what Go Backend does. So the receiver is essentially the same as stop and wait. Okay, so except it has actually a receive window size 1. We'll talk more about receive windows later. But we use a send window that have a size which is greater than 1, and we use a cumulative acknowledgements. So I'll get back to what that exactly means in a second. Now, I would like, before we start, to say, okay, there are many variations of this Go Backend protocol. So the variation we will talk about today is the one which is in the book. Okay, so if you read another book, you will find a slight deviation from the presentation here, most likely. But the core ideas are the same. Okay, so let's talk about the send window here. So this is the innovation. This is what changes from stop and wait, the send window. So we have an acknowledgement, and in the acknowledgement we have a acknowledgement number. Okay, let's call that ACNO. Okay, so if I'm the transmitter, I will send some packets, some frames like this, and then I will receive acknowledgements from the other end. So when I get an acknowledgement, I unpack it, I see if it's error-free, there is a number in that called the ACNO. Okay, and the ACNO tells me which packets have been delivered correctly. Okay, so if an error-free packet if an error-free acknowledgement arrives with some sequence number ACNO, then what do I do? Well, first of all, if the ACNO is too small, that is, it's less or equal to I think this is actually wrong here. So if ACNO is less than SF, or ACNO is greater or equal to Sn, then we ignore it. Because what we have in any particular point in time, we have a number of packets which are outstanding, and the oldest packet we have transmitted is the packet called SF. Actually, I'll take this back. Okay, so sorry about that. This is actually correct. Okay, so let me go through the protocol and then we can see that this is actually right, I hope. Okay, so if the ACNO is below or equal to SF or greater than Sn, then we just simply ignore it. Otherwise, we do something. We slide a window and we put SF equal to ACNO, and if SF is equal to Sn, then it means that now I think I want to change my mind again. So sorry about that. Give me 5 seconds. Or 10. 15 perhaps.
It should be if ACNO is equal to Sn, right? Because that's a packet that's empty.
Mm-hmm.
That can't have been delivered.
Yeah. Let me go and actually, I think it is like this, and if I change my mind, I'll let you know. But I think it should be less here, and then it should be greater or equal to this. No, it should be. Okay, we'll see. We'll see. Okay. So the thing is that if SF is equal to Sn, then there are no more outstanding packets, and we stop the timer. If SF is less than Sn, then there are at least one more outstanding packet, and we start the timer. Let's see if this makes sense. Okay, so we have here, before we get the acknowledgement, we have transmitted packet 7, 8, 9, and 10. If I then get an acknowledgement which is less than SF, how about this? We'll skip this slide and go to the example, because the example will define what is right and what is wrong. Sorry about this confusion. I wish I could say it's Monday morning, but it's not really. It's Monday afternoon. Okay, so let's go through an example and this will clear out. The thing is, what it really means is, okay, how should we interpret the ACNO? Okay, and there are several ways to do that. That's why I'm a little bit confused now. Okay, so let's see how Furusan does it. So an example, we have go back n here, and we have 3-bit sequence numbers, and we have a send size window of 7. Okay, so at any point in time, the transmitter can send up to 7 packets before it has filled up its send window. Okay, and since we are using 3-bit sequence numbers, we can numerate packets from 0 up to 6, so 0 up to 7, sorry, and then we start all over again. Okay, now let's start everything. So the initialization is to put SF equal to Sn, which means that the send window is empty. We haven't sent anything yet, and we put Rn, the state variable at the receive side, to be equal to 0 also. Okay, so this is the initialization. Okay, so now everything can start. So what can happen? Well, first of all, we have a higher layer that at some point in time will tell me, okay, here's a packet that I would like you to transmit. Okay, so if I'm the transmitter, I will get this packet, I will assign it a sequence number, and since it's the first one, it will get sequence number 0. And then I will send that packet. I will send the packet, and I will start the timer. Okay, so we get a request, we assign a sequence number, and this sequence number 0, it is what we transmit. Okay, so we transmit packet 0. And we start the timer. Okay, this packet goes over the channel, everything is okay. So the packet arrives here, the receiver checks it for errors, finds it to be error-free, and then then look at the sequence number, and the sequence number 0 is equal to Rn. Okay, so this is fine. Okay, so this is the sequence number of a packet that we would like to deliver. Okay, so we deliver this packet 0, and we increment deliver and increment Rn. Okay, so we take Rn, we was 0, and we make it into 1. Okay, this 1 we put as the ACNO in the acknowledgement that we sent back. Okay, so this is ACNO. So the acknowledgement then goes back to the transmitter. The transmitter checks the acknowledgement for errors and find it to be error-free, and then inspects the acknowledgement number that we got, 1. Okay, this is fine, because this tells us that the receiver would like to get a packet called 1, which implicitly says that he has received a packet which has number 0. Okay. Okay. So we check that the ACNO is greater than okay. So then what we do then is that we increment SF, okay? Because if the ACNO is 1, it means that the receiver would like to get a packet which has sequence number 0, sorry, sequence number 1, which means that they already received the one has sequence number 0. Okay. So now we see that the send window is empty, and then we stop the timer. Okay, so that was the first packet. Now suppose we then in sequence get 3 requests from the higher layer. Okay. For each request we assign the service data unit a sequence number which is 1, 2, or 3, and then we transmit these packet 1, packet 2, and packet 3 like this. Okay. Now notice here now that we transmit several packets without waiting for acknowledgements. And we keep on doing this until we either the timer expires or that we have filled up the send window, so we have no more space here. Okay. So what happens here? Well, packet number 1, okay, again, we have transmit the packet with sequence number 1. The receiver checks whether this is equal to the Rn it would like to see, and it said indeed it is, which means that we deliver and increment Rn. Okay. We put the request number into an acknowledgement, and we send the acknowledgement back. Now in this case the acknowledgement got lost. Is this disastrous? No, it turns out not to be in this case. Let's see what happens. Okay, packet number 2 is arrived. It is what the receiver is expecting. It's expecting packet number 2, so deliver an increment and then send back an acknowledgement now with acknowledgement number 3. Like this. Now this acknowledgement actually finds its way back to the sender without problems. So at this point in time, the sender checks the acknowledgement for errors. There are no errors. It then inspects the sequence number 3 and then see, okay, the sequence number is equal to 3, which means that 1 and 2 have been delivered. Okay. The sequence number that we get in acknowledgement, we can interpret that this is the next packet that the receiver would like to see. The sequence number of the next packet the receiver would like to see. And if the receiver would like to see 3, it means that it's no longer interested in 1 and 2, which means that 1 and 2 has been delivered. Is this clear now? Okay, so now we could, yes, good, question.
If 2 hasn't been delivered,
Mm-hmm.
will it send acknowledgement number 2 again?
Well, we'll see. On the next slide, we will see this. Okay. So this now, I mean, it's a special case that we look at now, but we'll see on the next slide what happens when we have errors in the frames also. Okay. Then, in the meantime, packet 3 is arriving at the transmitter, at the receiver, and we then see, okay, this is what we expect, and then send back an acknowledgement for 4, and at this point in time, we see that the receiver would like to get 4, which means that 3 has been delivered. Okay, and now we're back to an empty window here, and the process can start all over again. Okay, one thing which I did not mention here is what to do with the timer. So the timer starts when we start to transmit a packet, and every time we get an acknowledgement and slide the window, we restart the timer. Okay, and the timer will be used later on to trigger retransmission of packets which are in the send window. Okay, so now we should be able to figure out what was right on the slide before. So the acknowledgement should be, the ACNO here should be interpreted as the next packet that the receiver would like to see. Okay, so let's see now. Okay, how do I get rid of this? So the question is whether this is right. Okay, so when is an ACNO wrong? Well, the ACNO is wrong. We can slide the window if the acknowledgement number is greater than SF. Okay, because then it means that if ACNO is equal to 7, okay, that means that the receiver would like to see 7. The next packet he'd like to see is 7, but 7 is, I already transmitted that, and I cannot acknowledge that because the receiver still wants to see it. Okay, so I cannot do anything about that. I can slide the window, however, when the ACNO is equal to 8, then slide window. Okay, because if ACNO is equal to 8, that means that the receiver would like to see 8, which is the same thing to say I already gotten 7. Okay, so and if the ACNO is 9, it means that I would like to see 9, which means that I already seen 8 and 7, so we can release these. Okay, so as a matter of fact, we can ignore the acknowledgement when ignore ACK when ACK no, okay, is what? Less or equal to SF, right? Which I guess was standing there. I should have trusted my slides. Okay. Well, if on the other hand, the acknowledgement is greater than SN, it means that it expects a packet which is after a packet which I already have not been transmitted yet. So I can safely ignore that. Okay. Fine. Retransmissions then. What's going to happen? Well, in the Furusan version of Go Backend, there is a single timer that triggers the retransmissions. So if we get a timer that expires, then we send all the packets that are outstanding. Okay. So what does that mean? Well, let's go through an example here. And this might be a little bit small, but hopefully it's still visible. So again, we start by initializing everything. So we put SF equal SN equals 0, and we put RN equal to 0. We get the packet from the layer above, and we assign that to have sequence number 0, and we transmit packet 0, and then we get back an acknowledgement, and the acknowledgement is 1 in this case, meaning that I seen packet 0. I would like to have packet 1. Okay. So here everything works well. Now, suppose we get a new packet then we assign that to have sequence number 1, right? So we transmit packet number 1. This packet is lost. Okay, let's see what happens. Well, we get more packets from the layer above. We get packet number 2, packet number 3, and we transmit these. As packet number 2 goes over the channel, the receiver says, okay, here's an error-free packet, but the sequence number 2 is not what I expected. What I expect is Rn, which is equal to 1. Okay. So this means that this packet is out of order. Right? I was expecting 1 and I got 2. So I throw that packet away because I don't have space in my window. I cannot store it. I don't have space for it. But I would like to tell the transmitter, hey, something is wrong here. So I send back an acknowledgement here, but I use the same. I put always in here Rn, which is 1 in this case. Okay, the next packet that I get has sequence number 3, which is again not what I expect, because that's 1. And this one I put into the sequence number of the acknowledgement that I send back. Okay. What does the transmitter do here? Well, it's waiting for an acknowledgement, and in waiting for an acknowledgement which makes it possible to slide the window. But it's not possible here because we get acknowledgement 1 here, and 1 is equal to SF. Okay. So actually, Actually, at this point in time, the transmitter should be, thinking, here's something wrong. I sent a packet, and the receiver keeps on telling me that he wants that packet. Okay, so then this packet should be lost. Okay, but for some reason I keep on ignoring these acknowledgements because they have the wrong sequence number, and I just rely on that the timer, which was set at the outset of our first transmission here, will expire, and it will do that after some time, because the only time I reset, I start the timer when I transmit something, and I stop it or reset it when I get a correct acknowledgement back. Okay, so at this point in time, the timer expires, and what to do now? Well, we start all over again. We start to transmit packet 1, 2, 3 in succession, and hope for better luck this time. Okay, so packet 1 is resent, and we set an acknowledgement back. Now here, 1 is indeed equal to Rn, which means that I put Rn to 2, and then this 2 is what goes into the acknowledgement that's sent back. Next packet, resent, packet number 2, it arrives, acknowledgement packet 3, an acknowledgement with sequence number 3. We get packet 3 and we send it back like this. And now we have recovered. And at arrival of these acknowledgement, the transmitter can slide its window accordingly. And when the last acknowledgement has arrived, the send window is now empty and we can stop the timer. Okay. So we restart the timer whenever we get a correct acknowledgement back. And we stop the timer when the send window is empty. Here, when we received the wrong acknowledgements, we did not affect the timer. Okay. So any questions on this logic now? Did this explain your question? Good. Okay, excellent. No questions? Okay. This is a little bit complex, right? But if you look at a few examples of this, I'm sure you can figure out the logic of it. If we want to put down the logic in this state diagram form, which actually is more like it's a handy way to explain the logic behind everything. Okay. So remember that the state diagram has boxes which has states. So here we have the ready state and the blocking state. So these are the two states that the sender can be in. Okay. So, and then we should start something. And we remember that when we initialize, we go into the ready state and we put SF equal SN equals 0. Okay, so that's where we start. So what can happen in the ready state? A number of things can happen. We can, for instance, get a request from the process. Request from the process came. It sounds almost like Yoda saying this. Okay. So anyways, this means that the higher layer is giving us a packet to transmit. Okay. So what do we do then? Well, we make a packet with a sequence number equal to SN. Okay. We store a copy and we send the packet, and we start the timer if it's not already running, and we increment the SN state variable. Okay, and we go over along this branch. Now here there are two things that could happen. Either the window is full, the send window, that is SN is equal to SF plus S size. So this basically means that, okay, we don't have space for more packets to transmit. And then we go over to the blocking state. And the blocking state means that if I'm the transmitter here, I get packets from above, but when my send window is full, I just say stop, right? I don't accept anymore. So I'm now in the blocking state. And I have to wait until there is space in my send window before I can get more packets from above. All right. But suppose now that we have still space in our send window, then we go back to the ready state, and then we can accept another packet and we can transmit. We can send another packet, and we can go on like this until the send window is full. Okay. So we can go around this, or we can pop up in the blocking state here. But suppose we're here, still in the ready state, and if we have transmitted packets, we can also get acknowledgements. So if we get an error-free acknowledgement, okay, which has an ACNO greater or equal to SF and less than SN, okay, so it has the right sequence number, then we slide the window. And sliding the window is just to put SF equal to ACNO. And if ACNO is equal to SN, that means that the send window is empty, and then we stop the timer. If ACNO is less than SN, that means that we still have packets which are in transmission. We still have outstanding packets, and then we simply restart the timer. Okay. We can also get a corrupted acknowledgement or an acknowledgement, error-free acknowledgement, which has the wrong sequence number. So the ACNO is outside the send window, and then we just discard it. And finally, when we're in the ready state, we can get a timeout. And if we get the timeout, we resend all outstanding packets. All packets we have in the send window, we send them again in sequence. Start with the oldest one and then just transmit through them. And we restart the timer. Okay. Now, if we happen to be in the blocking state, and this can happen when we are transmitting a packet and the send window is full, and then we go into the blocking state, then essentially we can get a timeout again, and then we just retransmit the packets again. Or we get a corrupted acknowledgement, and then we cannot slide the window. Or we get an acknowledgement which is error-free but has the wrong sequence number, and we still cannot slide the window. So then we're back in the blocking state. The only way to get out from the blocking state is to be able to slide the window. And the slide the window, we can do that when we get an error-free acknowledgement with an acknowledgement number which is inside, points out that some of the outstanding packets have been received. Okay. So this is the sender side, and this is the complicated part of Go backend. The receiver is much simpler. But before explaining that, are there any questions on this logic here? No. Again, look at this, do a few examples, and I think the idea will fall down. Receiver is very simple. We start again by putting, we put in the start, we put rn equal to 0. Okay, so the first packet we expect is packet number 0. If we get a corrupt packet, okay, so there is only one state and it's ready. If we get a corrupted packet, we just throw it away. If we get an error-free packet with a sequence number which is equal to the one which we expected, then we deliver the message and then we slide the window, which is simply by incrementing rn and then send an acknowledgement with the incremented rn. If we get an error-free packet with the wrong sequence number, then we just discard it and we send an acknowledgement with the old, with the rn. So we don't increment rn in that case. Okay. So it's very simple. Any questions on this? This is like the stop and wait receiver also. It does the same thing. So, timeout. Well, for maximum efficiency, we would like to send, we would like to use the idle time at the transmitter side to make sure that we transmit packets whenever we have it. But we also need to send a, set the timeout, and we haven't talked about this. So let's talk about it. For maximum efficiency, when there is error-free, what should we do? Everything is error-free transmissions now, the best we can hope for. Then we should make sure that the send window size is large enough to avoid that we have an idle medium. Okay, so what is idle medium? It essentially means that, if we go back to the very first one, we should avoid being in a situation here where we can transmit packets, right? So we should avoid this. So then we put the send window size should be large enough to avoid this, and then we should put the timeout to be larger than the turnaround time to avoid unnecessary retransmissions. And why is this? Well, let's draw a timing diagram here. So we have the transmitter and we have the receiver for Go backend. And then at some point, we transmit the first packet and say that the packet size is TF as before. Then this packet is transmitted over the channel, is processed, and then an acknowledgement is sent back. And then that's processed, and at this point in time, this is what we defined as being the turnaround time or reaction time in the stop and wait situation. So this is the same thing in Go backend also. So here we have an information frame, and here we have an ACK frame. Okay. Now, what we would like to do now is to keep on sending packets. So we should send, if we have more packets to transmit, we should send the next packet here immediately. And then it goes over the channel and so forth, right? So we should make sure that we always transmit packets. Okay. Now, we also need to set the timeout. And the timeout should never be smaller than t0, because if the timeout is smaller than t0, we never give the acknowledgement enough time to reach the transmitter again. I mean, we need to allow for this t0 seconds to go before we trigger a retransmission. So the timeout should be greater than t0, and let's put the timeout to be the number of packets in the send window times tf. Okay, so maybe this is some time like this. If this is the case, then we can fit in total S-size frames before the timeout expires. And we would like to make S size T0 divided by TF. Okay, so the send window size should be large enough so we can fill the channel without being idle. And if this is not an integer, we round it up like this. Okay, so we would like the timeout to be greater than t0, and we can put it to equal to this if we put S size equal to this. Now, what would be the drawback of having a very large timeout? So what happens if the timeout is very large? Well, what will happen is that we keep on transmitting packets, and at some point, if we lose a frame, we will be in the blocking state, waiting for the timer to expire. And if we're in the blocking state and then we wait for the timer to expire, nothing happens. No new packets are transmitted and no new packets are acknowledged, which means that we increase the time it takes to deliver a frame, and then the effective rate will disappear. Yeah. Okay. So the moral of the story is that we would like to keep the timeout as small as possible, but not too small, right? And then we can, play around with that a little bit. Okay. Any questions before we break? No? Okay. So after the break, we will have this guest lecture about eHealth. So let's take, maybe 10 minutes if it's okay.